Um, we're very happy to have our next dot by Oktay Günlük. He is a Gary C. Butler Family Professor in the Georgia Tech in Industrial and Systems Engineering. He started his academic career. Well, no, he didn't start his academic career, but I don't know why this says that. He, I guess, he was most recently before Georgia Tech a professor of practice at Cornell University. Before that, he was a manager at the Mathematical Optimization Algorithms Group at IBM Research. Um, he also spent 3 years as a researcher in the OR group at AT&T Labs. His main interests are theoretical and computational aspects of discrete optimization problems. He is, I don't think this is listed in his bio, but he is also currently the editor in chief of Inform's Journal Optimization. At least not the bio that I put up online. I think might be on the bio that's on his website, which is probably better. He's currently the editor in chief of Inform's Journal on Optimization, and we're very pleased to have you, Oktay.
Okay, thank you very much, Alex. Nice introduction. A bit long, maybe. Uh, I want to start with thanking the organizers for putting together this seminar series, Sylvia, Claudia, and Alex. It's really nice, and thank you for the invitation. So today I'll talk about Dantzig-Wolfe decomposition and cutting planes. This is not brand new work. The paper has been published almost 2 years ago now. But I really like this topic because it's very basic, very simple, and hope you'll enjoy it. So the problem we're looking at is an integer program, which has this structure. So we're minimizing a linear function. A bunch of constraints are called block constraints that don't involve all of the variables. And then we have some coupling constraints and some integrality requirements. It's a fairly general setup. In this setting, we do not assume the index sets that are associated with the blocks to be disjoint. So there might be, overlaps, but these blocks typically have variables to themselves mostly, and then they might share variables with other blocks, or also there's a coupling constraints. Uh, we have these block polyhedra where, block constraints have to belong to. These are polyhedral sets, and we have integrality. So in the setting, we have all linear constraints and then integrality. And there are many, integer programming problems with this structure. I mean, the way I presented it is a fairly general structure. You can fit any integer program into this form. You can have empty blocks, for example. But this kind of a approach would make sense if blocks have some nice structure and have relatively fewer variables overlapping with the other blocks. So this is our formulation, and the constraint matrix, the way I see it, has this form. There are some coupling constraints, there are some common variables, there might be overlaps between blocks. So it's not a super clean structure, but there is some structure, and some of the problems that have been studied in the literature, like loosely coupled IPs where the blocks don't talk to each other, or two-stage stochastic programs where you don't have necessarily coupling constraints, and many others fit into this framework. So what do we do? So we have a MIP. We want to solve this integer program, and the best way we know how to do this is using relaxations, using branch and bound. The standard way to relax this problem is write the LP formulation by ignoring the integrality constraints. Instead of that, one can think about the Dantzig-Wolfe relaxation, where instead of saying that these block variables should belong to the block polyhedra, you require them to belong to the convex hull of integer points in that polyhedra. So this is clearly a better formulation. Here, I wrote it down for clarity. What I say Qj is points in the block polyhedra intersected with integrality. Okay, so clearly we have a smaller formulation if we use the Dantzig-Wolfe relaxation, and it will give us better bounds. So the name of the game here is to obtain better bounds for relaxations. So here's a little picture to repeat what I said. In the LP relaxation, we basically require block variables to belong to a polyhedra. In the Dantzig-Wolfe relaxation, we require them to belong to the convex hull of integer points in that polyhedron. Okay, so clearly we don't know how to define these convex hulls for general problems. But what we can do is we can reformulate the problem using additional variables and represent the convex hull of integer points in block polyhedra as a convex combination of extreme points of this convex hull and extreme rays of that convex hull. So what I did here is I replaced convex hull of Qj with convexification of the set using extreme points and extreme rays. So clearly, we don't want to enumerate all extreme points and extreme rays, and it's fairly standard that to solve this, one can use column generation. Okay, and then if you combine this with branching, you end up with a branch and price framework where you can keep on strengthening your Dantzig-Wolfe relaxation in the branches and do the enumeration. But as we all know, branch and price is quite expensive and messy. It requires a lot of effort, and even though it has been applied to special problem cases like vehicle routing, in general, it has not been a very robust approach. So let's look at column generation now. So we want to solve the Dantzig-Wolfe relaxation, but we don't want to go to branch and price to solve the integer program. That's the main idea. So how do we do the column generation? Okay, we start with a subset of the extreme points and extreme rays, and then we solve a restricted problem, look at the duals, and formulate a Pricean problem to generate the next extreme point or extreme ray for each black polyhedron, convex of integer points in the black polyhedron. And the Pricean problem looks like this. Sorry. Yeah, Pricean problem looks like this. You get the duals, sets of duals for each block, and you go solve an integer program. What's the best point in this block, integer point in this block, that would improve my formulation if I add it to this restricted problem. Okay? And once you get to the point where you can prove that there are no remaining extreme points and rays from these block problems, then you can prove optimality in the sense that you have your Dantzig-Wolfe bound. So far, so good. Actually, one thing I want to mention here is that when we're solving the problem with column generation, what we are doing really is building an inner approximation of the real set, Qj, this convex hull of integer points. Okay, we don't enumerate all the extreme points. We enumerate enough of them to attain the bound and prove that we don't need any more extreme points, extreme rays coming from these block problems. Okay, we know how to do this. Here's an example to motivate us more. So multiple knapsack assignment problem. Here you have items that have weight and profit. It's a general knapsack setup. Knapsacks can have different capacities. You have multiple knapsacks. And the twist here is that items have types. And in a knapsack, you can only pack items that are of the same type. And then your objective is to maximize the profit. So this is an example. So this knapsack, if it's assigned to books, it can be packed with books only. You cannot put, balls or peaches or anything like that. Okay. Now, this is a nice problem for our setup because it has a lot of blocks. These are the constraints for knapsack capacities. What it says is you have to assign a type to the knapsack, and then if that type is assigned to the knapsack, then the knapsack can be filled up to its capacity of items of that type. Okay, you pick a type for a knapsack, and then you say, okay, I can pack items of this type up to the capacity. And these are my coupling constraints, each, which items are assigned to which knapsack and which types are assigned to which knapsack. Okay, so these would be the blocks. And the nice thing is we have plenty of blocks. lots of blocks, but they're of course talking to each other. They're not, disjoint. These y's and x's appear in the coupling constraints and also other block constraints, block problems. Now, when you go apply the Dantzig-Wolfe bound to this problem, I have, bunch of problem cases here, different number of item types, different number of knapsacks, different number of items. And when we compare the improvements due to Dantzig-Wolfe bound, we see decent numbers. And in some cases, as dramatic as 50, 60%. So this idea of computing the Dantzig-Wolfe lower bound instead of the LP makes sense. It helps. But I'm slightly cheating here because what I'm comparing is the root LP bound and the Dantzig-Wolfe bound. When you throw a problem to a solver, it doesn't just solve the LP at the root node, it does whole bunch of magic, right? So when you do that, the numbers are not as dramatic, but still there is some benefit. So these are the problems where we had some improvement, more than 1% in these cases. And these are the old gap improvements, LP versus Dantzig-Wolfe. Here, I have the improvement after the root cuts, all the preprocessing and all the things that a solver does at the root. And clearly, you would expect this to be less dramatic, less improvement. But still, there are cases when you get a few more percentage improvement over the LP bound. So even with root cuts, this Dantzig-Wolfe bound has some potential. Okay, so we compute this bound. What do we do with it? Well, we want to solve a mixed integer program. Good bounds are good, but how are we going to use it in the enumeration framework? Okay, and as you remember, when we're solving the column generation formulation, we build an inner approximation of our problem, which means that when we terminate, the bound we find is valid, but the formulation at hand does not have all the rays and points. So this formulation is not valid. So we cannot put this into a solver and say that do branch and bound on this current formulation. If you want to use this, you have to do branch and price. You have to recompute the rays and vertices of these block polyhedra at each branch and bound node, which is not very desirable for obvious reasons. So, we have this bound. How can we incorporate it into the problem in its original formulation, original space? That's the next question. And one straightforward thing to do is to use objective function cuts. We have, value, lower bound on the objective function value. We can put this into the formulation as a cutting plane. It is valid. And this would recover the bound. Except it is a terrible idea computationally. Because when you throw it into the solver, this kind of cut, solvers get seriously confused. Their cutting planes, branching decisions are all over the place. And the branch and bound tree grows larger than it would if you haven't put in this single objective function cut. And a possible explanation is this simple lemma with simple observation. If you're throwing at a non-trivial cut to a polyhedron, and it's an objective cut, this creates an optimal phase, LP optimal phase, with dimension basically almost as large as the polyhedron itself. Ed has a question. Ed, do you want to ask?
Yes. Our consensus as to at least part of the reason that happens is that when you add a cut like this, it really hurts the pseudo cost calculations in the branching. That's not to say that what you're saying also is not true, but that has been our view as to the primary reason for the problematic performance that you're pointing out right now.
I see. You don't think cutting planes also gets confused at the same time?
It could be that as well.
That's
been the primary focus, so that basically all the pseudo cost information is basically lost.
Yeah.
So that we've always used that as the primary source.
Okay. Yeah. Thank you. Thank you. So okay, so we have some agreements from people who really know how the solvers work. So this is a terrible idea. What can we do? So the bound we obtain is obtained by solving this problem, right? We have the coupling constraints, and instead of the polyhedra, we put in the convex hull of integer points. But this object is a polyhedra itself, right? It has, facets. So in theory, if you add all the facets of this Qj, you can obtain the same bound without having to use the objective function cut. Of course, we're not going to do this. But with this observation, we say a cutting plane is a block cut if it is strictly, it can strictly be associated with one of the blocks, meaning that the cut, the valid inequality, uses block variables from one block only, okay? And the right-hand side is the solution kind of to the pricing problem for that particular pi, constraint coefficients, where you go, it's a fan shell cut, basically. You go look at the best point, best integer point in that block structure and its value, and then you say none of the points in that block can attain a better value than this with respect to this constraint coefficients. Now, if we add all block cuts, we will recover the Dantzig-Wolfe bound. That's great, but we don't want to find all the block cuts. So, how can we help with this? Our solution is not very surprising. So we observe that when we're doing column generation, we keep on generating these extreme points and extreme rays. And to do that, we solve the pricing problem, which is of this form. Given some dual values, what's the best point we can get from this block problem? Now, when we solve the problem and find a new point to add our column generation, we are also obtaining a valid inequality for the problem. Each point comes with a Fanchel cut that actually tells us something about that polyhedron. Okay? Now, in other words, each time we generate a column, we generate a point, it also comes with a valid inequality for the convex hull of integer points there. So we can think of column generation as building an inner approximation to obtain the Dantzig-Wolfe bound, but also we can see the process as generating valid inequalities for the original problem and building an outer approximation. Okay? So this is a good thing because this is happening in the original space of variables. Okay? This is something we can use. And the punchline of this is, if you carry on your column generation, solving these pricing problems, bringing in vertices and rays of the convex hull of integer points in these blocks, and at the end, if you stop and say that, okay, there is nothing left, no more vertices, no more rays, I solve the Dantzig-Wolfe relaxation, the cuts you obtain from the last iteration actually give you the Dantzig-Wolfe bound in the original space. So these are my, coupling constraints. This is the original problem objective function. And here what I have is one cut per block. And these cuts are the final iteration, cuts coming from the column generation. The last point, you generate during column generation, you take the cut associated with it, the Fanchel cut, and you just add those to your formulation, and you recover the bound. Okay? So this is, in some ways, you can see this as disaggregating the objective function cut and associating pieces of it to different blocks. Okay, so instead of one cut, we get one cut per block now, and we, obtain the Dantzig-Wolfe bound. So now our strengthened formulation then would become this. I have the original block constraints, polyidal constraints. I have the coupling constraints integrality. And now I added these block cuts, one cut per block. Okay? And if we solve the LP relaxation of this formulation with the additional block cuts, it will give us the same bound as the Dantzig-Wolfe decomposition. And this formulation is in the original space. So that's a good thing. So I have a couple of computational tables now to show that this idea is not a bad idea at all. So what I have here is a bunch of problem instances. There are 30 instances for each group, and each group has different item types, knapsack, number of knapsacks and items. So this first column is out of the number of instances solved out of 30 test instances using the original formulation with Groby. Okay. The second column is the same formulation augmented with the objective function cut that comes from the Dantzig-Wolfe relaxation. And you can see that the number of solved instances go down. So objective function cut is a terrible idea. And the next column here is using these block cuts instead of the objective function cut, one cut per block. And you see that you actually do better than the original MIP formulation. These cuts do not degrade the enumeration process like the objective function cut. Instead, it improves it. Okay? So next, now we have these cuts, block cuts. We don't have to use them as they are. We know cutting planes. We know how to strengthen cutting planes if we have valid cutting planes in hand. And using these ideas, these things from the literature with some twists, we apply two kinds of strengthening to the block cuts that we obtain during the process. First one is disjunctive cut strengthening. So I did not get into the details of these cuts, but once we generate an extreme point of this block polyhedra and the cut associated with it, we know that there are some points in the problem that are tight on this valid inequality, but with a certain parity. A certain variable is, we know that a certain variable with value 1, if it's a binary problem, I'm talking about binary problems here in this strengthening idea. If it's 1, then what happens if it's 0? And perhaps you can tilt it a little bit and to make it stronger. So in a small picture, if this is your block polyhedron, you would be generating a cut like this. And if your variables are binary, there are ways to tilt this and then turn it into a higher dimensional face of the block polyhedron. Okay, this has been earlier used by Anderson and Poche, and we apply this idea to sequentially strengthen each cut coefficient. A second idea is a little bit more complicated. It involves replacing one valid inequality with two that together imply the first one, and also give you a smaller feasible region. So I have details of these, but I don't want to go into them right now. So once you apply these ideas, the computational performance actually increases. So now I have four columns here. I throw out the objective function cut because it's a terrible idea. This is the MIF formulation. This is our block cuts. This is after strengthening, variable coefficient strengthening for each cut. And this is on top of that also doing tilting. So what you see is strengthening, which is a fairly cheap operation, actually improves noticeably in these harder problems the computational performance of the procedure. So, tilting idea, which is a more expensive operation because it also increases the number of valid inequalities significantly, almost exponential, depending on how many times you do the tilting. it does help, but it does help in harder problems and slows you down in easier problems. Okay, so the conclusion here is that it's a good idea to get these block cuts. It gives you a better bound. Computationally, it helps. And one should not use the block cuts as they are. Try to strengthen them using known techniques we have in cutting plane computational experiences. And this joint approach can actually improve over standard solvers. So there is one more slide I want to show you. I didn't mention, sorry. This is joint work with Andrea Lodi and Ray Chen. Andrea loves machine learning. So we had to have a section that talks about machine learning, and that's kind of the rule these days. Every paper, every talk has to have something about machine learning or quantum computing for that matter. Anyway, so what we do here is that, all right, so, these cuts do well, but not on all problems. In some problems, the original solver does better than us. In aggregate, these cuts are doing better. What we did was we picked 20% of the problem instances and, trained our complicated machine learning algorithm by solving them with and without the block cuts. And then we labeled them as, use block cuts, don't use block cuts, based on the performance. If the cuts improve the performance, improves the gap at termination, or they are 10% faster to optimality, we say those instances are good for block cuts. And then we, recorded simple features of the problems, like what's the LP bound, what's the Dantzig-Wolfe bound, what is the LP bound after adding cutting planes, and such. And then we, run this deep neural network, and that's a joke, to obtain this super simple rule, which says that if the improvement of the Dantzig-Wolfe bound over the LP bound scaled by an upper bound is more than 0.05%, use block cuts. Now, once we actually implement this on the remaining 80% of the instances, we realize that we actually do improve over the standard. So MIP solves 167 instances, R cut 106. If you do the simple ML type of rule, you increase the number of instances you solve and improve on the time. Okay? So, and one other thing, these instances now are a union of the two solved instance classes by two methods. So in these two, there are problems that MIP solves, but Dantzig-Wolfe doesn't, or vice versa. But in this one, we actually capture all of the problems that can be solved by either method. So with that, I want to say one more thing. I know I'm out of time. I talked about column generation. Vanilla column generation doesn't work. It doesn't, converge, as you might all guess. Instead of solving that, we formulate a Lagrangian relaxation of the problem, and then use the level method to solve it. And this approach converges quickly, and all the numbers I showed you earlier is, obtained by using this method. And at this point, I will stop and thank you.
So I think that since we are roughly right on time, and there's also the opportunity to join into breakout rooms, I think maybe the best thing to do would be to thank both speakers now, Oktay and Claudia, for today. And I should mention that we will have these breakout rooms now for the next however much time anybody wants to chat with the individual speakers, and we'll break out first individually and then maybe merge them together. We have another set of dots coming in a month, I believe. I don't remember the exact date. Maybe Margarita remembers.
Yes, at the end of the month. So
April 24th.
Yes.
If my memory serves me correctly. So we hope to see you there. Last thing I should say is we don't always acknowledge this, but we are part of the Mixed Integer Programming Society. This is one of the events, and we are also holding part of the Mixed Integer Programming Society, the Mixed Integer Programming Workshop. Not we, a whole different group of people. That's going to be in Connecticut in a month and a half. Registration is open, and there's also a call for flash talks in case you want to be considered for selection to the contributed talks that are done at the Mixed Integer Programming Workshop. So in case you're interested, look on the Mixed Integer Programming website, and you should see some things about the workshop there as well. So anyway, thank you all for attending, and I'll see you all in the breakout rooms now.